Magnitude lower density. Jet or rocket engine mass thrust to. Weight ratio. Kilogram, pound, kn, lbf. Road 0410 nuclear rocket engine 4435.27,901.8. J58 jet engine, SR-71 Blackbird, 2722 6001 150 34,005.2. Rolls-Royce /Snecma Olympus 593. Turbojet with reheat, Concorde, 3175 7169.2 38,005.4. Pratt & Whitney F119 1800 3991 20,507.95. Road 0750 rocket engine, 3 propellant mode 4621 10,188 1413 318,031.2. Road 0146 rocket engine 260 570 98 22,038.4. Rocketdyne RS-25 rocket engine 3177 7004 2278 512,073.1. Road 180 rocket engine 5393 11,894,152 933,078.5. Road 170 rocket engine 9750 21,507,887 1,773,082.5. F1 Saturn V first stage 8,391 18,499 7,740.5 1,740,194.1. NK-33 rocket engine 1222 2694 1638 368,136.7. Merlin 1D rocket engine, full thrust version 467 103825 185,180.1. Of the liquid fuels used, density is lowest for liquid hydrogen. Although hydrogen /oxygen burning has the highest specific impulse of any in-use chemical rocket, hydrogen's very low density, about 1/14 that of water, requires larger and heavier turbo pumps and pipe work, which decreases the engine's thrust-to-weight ratio, for example the RS-25. Compared to those that do not use hydrogen, NK-33. Mechanical issues, edit. Rocket combustion chambers are normally operated at fairly high pressure, typically 10-200 bar, 120 MPa, 153,000 psi. When operated within significant atmospheric pressure, higher combustion chamber pressures give better performance by permitting a larger and more efficient nozzle to be fitted without it being grossly overexpanded. However, these high pressures cause the outermost part of the chamber to be under very large hoop stresses. Rocket engines are pressure vessels. Worse, due to the high temperatures created in rocket engines, the materials used tend to have a significantly lowered working tensile strength. In addition, significant temperature gradients are set up in the walls of the chamber and nozzle. These cause differential expansion of the inner liner that create internal stresses. Hard starts, edit. A hard start refers to an overpressure condition during start of a rocket engine at ignition. In the worst cases, this takes the form of an unconfined explosion, resulting in the damage or destruction of the engine. Rocket fuels, hypergolic or otherwise, must be introduced into the combustion chamber at the correct rate in order to have a controlled rate of production of hot gas. A hard start indicates that the quantity of combustible propellant that entered the combustion chamber prior to ignition was too large. The result is an excessive spike of pressure, possibly leading to structural failure or explosion. Avoiding hard starts involves careful timing of the ignition relative to valve timing or varying the mixture ratio so as to limit the maximum pressure that can occur, or simply ensuring an adequate ignition source is present well prior to propellant entering the chamber. Explosions from hard starts usually cannot happen with purely gaseous propellants, since the amount of the gas present in the chamber is limited by the injector area relative to the throat area, and for practical designs, propellant mass escapes too quickly to be an issue. A famous example of a hard start was the explosion of Wernher von Braun's 1W engine during a demonstration to General Walter Dornberger on the 21st of December, 1932. Delayed ignition allowed the chamber to fill with alcohol and liquid oxygen, which exploded violently. Shrapnel was embedded in the walls, but nobody was hit. Acoustic issues, edit. The extreme vibration and acoustic environment inside a rocket motor commonly result in peak stresses well above mean values, especially in the presence of organ pipe-like resonances and gas turbulence. Combustion instabilities, edit. The combustion may display undesired instabilities, of sudden or periodic nature. The pressure in the injection chamber may increase until the propellant flow through the injector plate decreases. A moment later the pressure drops and the flow increases, injecting more propellant in the combustion chamber, which burns a moment later, and again increases the chamber pressure, repeating the cycle. This may lead to high-amplitude pressure oscillations, often in ultrasonic range, which may damage the motor. Oscillations of plus or minus 200 psi at 25 kHz were the cause of failures of early versions of the Titan II missile second-stage engines. The other failure mode is a deflagration to detonation transition. The supersonic pressure wave formed in the combustion chamber may destroy the engine. Combustion instability was also a problem during Atlas development. The Rocketdyne engines used in the Atlas family were found to suffer from this effect in several static firing tests, and 3 missile launches exploded on the pad due to rough combustion in the booster engines. In most cases, it occurred while attempting to start the engines with a dry start method whereby the igniter mechanism would be activated prior to propellant injection. During the process of man-rating Atlas for Project Mercury, solving combustion instability was a high priority, and the final 2 Mercury flights sported an upgraded propulsion system with baffled injectors and a hypergolic igniter. The problem affecting Atlas vehicles was mainly the so-called racetrack phenomenon, where burning propellant would swirl around in a circle at faster and faster speeds, eventually producing vibration strong enough to rupture the engine, leading to complete destruction of the rocket. It was eventually solved by adding several baffles around the injector face to break up swirling propellant. More significantly, combustion instability was a problem with the Saturn F1 engines. Some of the early units tested exploded during static firing, which led to the addition of injector baffles. In the Soviet space program, combustion instability also proved a problem on some rocket engines, including the Rode 107 engine used in the R-7 family and the Rode 216 used in the R-14 family, and several failures of these vehicles occurred before the problem was solved. Soviet engineering and manufacturing processes never satisfactorily resolved combustion instability in larger RP-1 /LOX engines. So the Rode 171 engine used to power the Zenit family still used 4 smaller thrust chambers fed by a common engine mechanism. The combustion instabilities can be provoked by remains of cleaning solvents in the engine. For example, the first attempted launch of the Titan II in 1962, reflected shock wave, initial instability after ignition, explosion near the nozzle that reflects into the combustion chamber, and many more factors. In stable engine designs, the oscillations are quickly suppressed. In unstable designs, they persist for prolonged periods. Oscillation suppressors are commonly used. 3 different types of combustion instabilities occur. Chugging, edit. A low-frequency oscillation in chamber pressure below 200 Hz. Usually it is caused by pressure variations in feed lines due to variations in acceleration of the vehicle, when rocket engines are building up thrust, are shut down or are being throttled. Chugging can cause a worsening feedback loop, as cyclic variation in thrust causes longitudinal vibrations to travel up the rocket, causing the fuel lines to vibrate, which in turn do not deliver propellant smoothly into the engines. This phenomenon is known as pogo oscillations or pogo, named after the pogo stick. In the worst case, this may result in damage to the payload or vehicle. Chugging can be minimized by using several methods, such as installing energy-absorbing devices on feed lines. Chugging may cause screeching. Buzzing, edit. An intermediate frequency oscillation in chamber pressure between 200 and 1000 Hz. Usually caused due to insufficient pressure drop across the injectors. It generally is mostly annoying, rather than being damaging. Buzzing is known to have adverse effects on engine performance and reliability, primarily as it causes material fatigue. In extreme cases, combustion can end up being forced backwards through the injectors. This can cause explosions with monopropellants. Buzzing may cause screeching. Screeching, edit. A high-frequency oscillation in chamber pressure above 1000 Hz, sometimes called screaming or squealing. The most immediately damaging, and the hardest to control. It is due to acoustics within the combustion chamber that often couples to the chemical combustion processes that are the primary drivers of the energy release, and can lead to unstable resonant screeching that commonly leads to catastrophic failure due to thinning of the insulating thermal boundary layer. Acoustic oscillations can be excited by thermal processes, such as the flow of hot air through a pipe or combustion in a chamber. Specifically, standing acoustic waves inside a chamber can be intensified if combustion occurs more intensely in regions where the pressure of the acoustic wave is maximal. Such effects are very difficult to predict analytically during the design process, and have usually been addressed by expensive, time-consuming and extensive testing, combined with trial and error remedial correction measures. Screeching is often dealt with by detailed changes to injectors, changes in the propellant chemistry, vaporizing the propellant before injection, or use of Helmholtz dampers within the combustion chambers to change the resonant modes of the chamber. Testing for the possibility of screeching is sometimes done by exploding small explosive charges outside the combustion chamber with a tube set tangentially to the combustion chamber near the injectors to determine the engine's impulse response, and then evaluating the time response of the chamber pressure. A fast recovery indicates a stable system. Exhaust noise, edit. Main article, acoustic signature. For all but the very smallest sizes, rocket exhaust compared to other engines is generally very noisy. As the hypersonic exhaust mixes with the ambient air, shock waves are formed. The Space Shuttle generated over 200 dB of noise around its base. To reduce this, and the risk of payload damage or injury to the crew atop the stack, the mobile launcher platform was fitted with a sound suppression system that sprayed 1.1 million liters, 290,000 US of water around the base of the rocket in 41 seconds at launch time. Using this system kept sound levels within the payload bay to 142 dB. The sound intensity from the shock waves generated depends on the size of the rocket and on the exhaust velocity. Such shock waves seem to account for the characteristic crackling and popping sounds produced by large rocket engines when heard live. These noise peaks typically overload microphones and audio electronics, and so are generally weakened or entirely absent in recorded or broadcast audio reproductions. For large rockets at close range, the acoustic effects could actually kill. More worryingly for space agencies, such sound levels can also damage the launch structure, or worse, be reflected back at the comparatively delicate rocket above. This is why so much water is typically used at launches. The water spray changes the acoustic qualities of the air and reduces or deflects the sound energy away from the rocket. Generally speaking, noise is most intense when a rocket is close to the ground, since the noise from the engines radiates up away from the jet, as well as reflecting off the ground. Also, when the vehicle is moving slowly, little of the chemical energy input to the engine can go into increasing the kinetic energy of the rocket, since useful power P transmitted to the vehicle is P equals F asterisk V. For thrust F and speed V. Then the largest portion of the energy is dissipated in the exhaust's interaction with the ambient air, producing noise. This noise can be reduced somewhat by flame trenches with roofs, by water injection around the jet and by deflecting the jet at an angle. Rocket Engine Development, edit. United States, edit. The development of the U.S. rocket engine industry has been shaped by a complex web of relationships between government agencies, private companies, research institutions, and other stakeholders. Since the establishment of the first liquid propellant rocket engine company, Reaction Motors, Inc., in 1941 and the first government laboratory, GALCIT, devoted to the subject, the U.S. liquid propellant rocket engine, LPRE, industry has undergone significant changes. At least 14 U.S. companies have been involved in the design, development, manufacture, testing, and flight support operations of various types of rocket engines from 1940 to 2000. In contrast to other countries like Russia, China, or India, where only government or pseudo-government organizations engage in this business, the U.S. government relies heavily on private industry. These commercial companies are essential to the continued viability of the United States and its form of governance, as they compete with one another to provide cutting-edge rocket engines that meet the needs of the government, the military, and the private sector. In the United States, the company that develops the LPRE usually is awarded the production contract. Generally, the need or demand for a new rocket engine comes from government agencies such as NASA or the Department of Defense. Once the need is identified, government agencies may issue requests for proposals, RFPs, to solicit proposals from private companies and research institutions. Private companies and research institutions, in turn, may invest in research and development, R&D, activities to develop new rocket engine technologies that meet the needs and specifications outlined in the RFPs. Alongside private companies, universities, independent research institutes and government laboratories also play a critical role in the research and development of rocket engines. Universities provide graduate and undergraduate education to train qualified technical personnel, and their research programs often contribute to the advancement of rocket engine technologies. More than 25 universities in the U.S. have taught or are currently teaching courses related to liquid propellant rocket engines, LPREs, and their graduate and undergraduate education programs are considered one of their most important contributions. Universities such as Princeton University, Cornell University, Purdue University, Pennsylvania State University, University of Alabama, the Navy's Postgraduate School, or the California Institute of Technology have conducted excellent R&D work on topics related to the rocket engine industry. One of the earliest examples of the contribution of universities to the rocket engine industry is the work of the GALCIT in 1941. They demonstrated the first jet-assisted takeoff, JATO, rockets to the Army, leading to the establishment of the Jet Propulsion Laboratory. However, the transfer of knowledge from research professors and their projects to the rocket engine industry has been a mixed experience. While some notable professors and relevant research projects have positively influenced industry practices and understanding of LPREs, the connection between university research and commercial companies has been inconsistent and weak. Universities were not always aware of the industry's specific needs, and engineers and designers in the industry had limited knowledge of university research. As a result, many university research programs remained relatively unknown to industry decision-makers. Furthermore, in the last few decades, certain university research projects, while interesting to professors, were not useful to the industry due to a lack of communication or relevance to industry needs. Government laboratories, including the Rocket Propulsion Laboratory, now part of Air Force Research Laboratory, Arnold Engineering Test Center, NASA Marshall Space Flight Center, Jet Propulsion Laboratory, Stennis Space Center, White Sands Proving Grounds, and NASA John H. Glenn Research Center, have played crucial roles in the development of liquid rocket propulsion engines, LPREs. They have conducted unbiased testing, guided work at U.S. and some non-US contractors, performed research and development, and provided essential testing facilities including hover test facilities and simulated altitude test facilities and resources. Initially, private companies or foundations financed smaller test facilities, but since the 1950s, the U.S. government has funded larger test facilities at government laboratories. This approach reduced costs for the government by not building similar facilities at contractors' plants but increased complexity and expenses for contractors. Nonetheless, government laboratories have solidified their significance and contributed to LPRE advancements. LPRE programs have been subject to several cancellations in the United States, even after spending millions of dollars on their development. For example, the MLLOX/LH2 LPRE, Titan I, and the RS-2200 Aerospike, as well as several JATO units and large uncooled thrust chambers were cancelled. The cancellations of these programs were not related to the specific LPRE's performance or any issues with it. Instead, they were due to the cancellation of the vehicle programs the engine was intended for or budget cuts imposed by the government. USSR, edit. Russia and the former Soviet Union was and still is the world's foremost nation in developing and building rocket engines. From 1950 to 1998, their organizations developed, built, and put into operation a larger number and a larger variety of liquid propellant rocket engine, LPRE, designs than any other country. Approximately 500 different LPREs have been developed before 2003. For comparison, the United States has developed slightly more than 300 before 2003. The Soviets also had the most rocket-propelled flight vehicles. They had more liquid propellant ballistic missiles and more space launch vehicles derived or converted from these decommissioned ballistic missiles than any other nation. As of the end of 1998, the Russians, or earlier the Soviet Union, had successfully launched 2,573 satellites with LPREs, or almost 65% of the world total of 3,973. All of these vehicle flights were made possible by the timely development of suitable high-performance reliable LPREs. Institutions and actors, edit. Unlike many other countries where the development and production of rocket engines were consolidated within a single organization, the Soviet Union took a different approach. They established numerous specialized design bureaus, DB, which would compete for development contracts. These design bureaus, or Konstruktorskoye Bureau, KB, in Russian, were state-run organizations which were primarily responsible for carrying out research, development and prototyping of advanced technologies usually related to military hardware, such as turbojet engines, aircraft components, missiles, or space launch vehicles. Design bureaus which specialized in rocket engines often possessed the necessary personnel, facilities, and equipment to conduct laboratory tests, flow tests, and ground testing of experimental rocket engines. Some even had specialized facilities for testing very large engines, conducting static firings of engines installed in vehicle stages, or simulating altitude conditions during engine tests. In certain cases, engine testing, certification and quality control were outsourced to other organizations and locations with more suitable test facilities. Many DBS also had housing complexes, gymnasiums, and medical facilities intended to support the needs of their employees and their families. The Soviet Union's LPRE development effort saw significant growth during the 1960s and reached its peak in the 1970s. This era coincided with the Cold War between the Soviet Union and the United States, characterized by intense competition in spaceflight achievements. Between 14 and 17 design bureaus and research institutes were actively involved in developing LPREs during this period. These organizations received relatively steady support and funding due to high military and spaceflight priorities, which facilitated the continuous development of new engine concepts and manufacturing methods. Once a mission with a new vehicle, missile or spacecraft, was established, it was passed on to a design bureau whose role was to oversee the development of the entire rocket. If none of the previously developed rocket engines met the needs of the mission, a new rocket engine with specific requirements would be contracted to another DB specialized in LPRE development. Oftentimes each DB had expertise in specific types of LPREs with different applications, propellants, or engine sizes. This meant that the development or design study of a rocket engine was always aimed at a specific application which entailed set requirements. When it comes to which DBS were awarded contracts for the development of new rocket engines, either a single design bureau would be chosen or several design bureaus would be given the same contract, which sometimes led to fierce competition between DBS. When only one DB was picked for the development, it was often the result of the relationship between a vehicle or systems chief designer and the chief designer of a rocket engine's specialized DB. If the vehicle's chief designer was happy with previous work done by a certain design bureau, it was not unusual to see continued reliance on that LPRE bureau for that class of engines. For example, all but one of the LPREs for submarine-launched missiles were developed by the same design bureau for the same vehicle development prime contractor. However, when two parallel engine development programs were supported in order to select the superior one for a specific application, several qualified rocket engine models were never used. This luxury of choice was not commonly available in other nations. However, the use of design bureaus also led to certain issues, including program cancellations and duplication. Some major programs were cancelled, resulting in the disposal or storage of previously developed engines. One notable example of duplication and cancellation was the development of engines for the R-9, a ballistic missile. 2 sets of engines were supported, but ultimately only one set was selected, leaving several perfectly functional engines unused. Similarly, for the ambitious Heavy NL space launch vehicle intended for lunar and planetary missions, the Soviet Union developed and put into production at least 2 engines for each of the 6 stages. Additionally, they developed alternate engines for a more advanced NL vehicle. However, the program faced multiple flight failures, and with the United States successfully